Hey folks, well let's continue our discussion of control flow selection statements, and we were talking about multiple selection. So what I want to do now is just think about the switch case type statement versus the if statement for multiple selection. So if you're in a situation with a switch case statement, you're always doing some switch about some value. Hang on one second here. There we go. Okay, so you're switching around some value. So the problem is this value basically gets resolved into a constant. Now the thing that's nice about an if statement is that makes it sort of superior to a switch and case statement is that you can have an if statement based on a Boolean expression, but the Boolean expression itself can contain all kinds of different numeric and other types of operations on it. So here we're either getting true or false, but I could say if x is less than 10, then I want to do this. And then someone actually brought this up in class. This is a way of doing multiple selection. Else if x is less than 100, then do this. Else if x is less than 1,000, then do this. So this is kind of interesting because there's no way that you can have this type of expression in a switch case statement, because the value that we have, the value here, also always has to resolve into some type of constant. Alright, well that's all I want to say about selection statements. That was a quick wrap-up of that discussion from class, and just a little bit of extra notes bringing in multiple selection using the if-else construct. Now what I'm going to do is talk about repetition. Now we're going to focus on repetition by only looking at iteration as a form of repetition. There's actually two ways that you can do repetition. One is through iteration, and the other way is through recursion. And when we explore scheme later on in the course, we're going to mess around with recursion. But for right now, we're just going to focus on iterative forms of repetition. So for iteration, there's two flavors of iteration. So flavor number one is called counter-controlled iteration, and flavor two is logically controlled, or logic controlled. I want to use good parallel form there. Logic controlled iteration. So for counter-controlled, consider this loop. In Java, it would be something like this. For int I equals 0, I is less than 10, I plus plus, and you do some stuff. Okay. So now you know what the name of that type of loop is. It's called a counter-controlled loop. Now, something that's interesting, an interesting question, a couple of interesting questions to ask here are, number one, what is the scope of the counter. Okay, so what is the scope of I here? So the answer to that is actually kind of an important thing to figure out, because depending on the language you're working with, in fact, depending on the compiler sometimes that you're working with, the answer to this question is not trivial. And why does that become important? Well, if you're developing habits of programming, like I have, you fall into certain patterns when you do counter-controlled loops. One of the things I do is I try in every situation to always have my for loops use I as the name of the counter-controlled variable in my counter-controlled loops. Why? Because I don't want to think of any other names. It hurts my brain to do that. And so I've just gotten in the habit of always using I. That's really nice, because usually whenever I see I anywhere in any program, I know that that I belongs, that any program that I've written, I know that I probably belongs to a counter-controlled loop. Now, you might be saying, so what? Well, it does become a big deal if you try to do this all the time when you construct the initial value of your counter-controlled variable. So in this case, I'm saying int I equals 0. So I'm declaring I, and my intention is to declare I as part of this block right here. So I belongs, or I has the scope of the block of code that's inside the for loop. I does not exist out here, and I does not exist out here. So once the for loop ends and this block goes away, then I goes away. So that's kind of interesting. Now, again, why is that important? Well, if the scope of I is not this block here, if it's not the block, and the scope of I is in fact outside the block, then a couple of things become important. So this is the scope now. So let's say the scope's outside the block. One thing it means is that every time I try to do this for loop, for int I equals 0, if that's how I do every for loop, and by the way, that's pretty much how I do every for loop, I'm going to get a compiler error the second time I try to say for int I equals 0. And that is really annoying, because then I have to go back through my code and edit it. But the thing is, what I have to make sure of is that some of my for loops say for int I equals 0, and that's because those for loops are declaring I for the first time inside whatever block the for loop's in. And then some of our for loops cannot say for int I equals 0 because I's already been declared somewhere in another for loop in the same block of code. So I don't like to have to keep track of all that stuff. I'd rather just say for int I equals 0 all the time. So the answer to scope is it depends on the language. Okay, for Java, it's I is declared, considered to have been declared inside the scope of the for loop block. It's not declared outside the scope of the for loop block. So if you try to say system.println I here, you get an error. All right. I've had experience with C++ compilers where, and this is a while ago, but I'm sure there's compilers that will give you this kind of experience. Depending on which compiler you use, I will either behave like Java, or it'll behave like the first time you declare I in the first for loop in a block of code. That's where I is declared, and then everywhere else you can't declare I because it's already been declared if you're declaring for loops in the same block. All right, second question is, can you change the value of the counter inside the body of the loop? In other words, can you change the value in here? Well, I mean, clearly it's being changed up here, but can you change it here? Well, if you're programming in Java or any of the C-based languages, the answer is yes, you can change it. But there are some languages that don't let you do this. For example, Fortran. So we'll look at an example of Fortran in a second. Another question is, can you change the value of loop parameters? So what are loop parameters? They're the things that might influence how a loop executes. So here I'm initializing I to a particular value, but I don't have to initialize I to 0, a constant. I can initialize I to some value, let's say k. And I'm saying here I is less than 10, but what if I say I is less than j? So the question is, if I change the value of k here and j here, will that influence how many times the loop has to execute? And the answer to that question is, it depends on the language that you're looking at. So let's take a look at Fortran to answer these questions of, can you change the value of a counter in a loop, and can you change the value of loop parameters? Let me bring this down here. So here's some Fortran code. Do 10 I equals 1, 30, 2. So this means start I at 1. We're going to end I if it is greater than this value of 30, and we're going to step in increments of 2. And then what we're going to do is I'm going to say write I, 20, and format I for 4-byte integer, and this 20 goes here on this line with the format, and then we're going to say 10 continue, and that's really the end of the loop. Okay, so here's a counter control loop in Fortran. Now, how many iterations does the loop perform? Well, the answer to that is it performs 15 iterations. We start at 1, and then we go to 3, then 5, all the way up to 29. So it doesn't perform any more than that, because once I gets, you add 2 more to I, now I is 31, and it's greater than 30, so we're going to end at when I has the value of 29. Now, how many iterations does the loop perform? Oh yeah, I said that, 15. All right, so it turns out that you can derive a general equation for computing the number of iterations. So if you want to try a good exercise to test your chops, try and derive that. So the things you're going to look at are what is the initial value, what's the terminal value, the start, the end, what's the step. Okay, and so take a second, you can pause this if you want to see if you can come up with it. Okay, so the solution to this is you're going to take the max of truncate, the following. So initial, maybe what I'll do to make this more consistent, I'm going to go back here for a second, erase this, right? Start, stop, step. Sounds nice. Start, stop, step. Okay. So you're going to take the stop value and subtract the initial value, or sorry, the start value from that, and you're going to add the step value to that. Okay. And you're going to divide that by that whole expression, this whole expression, by the step. So that's going to give you the number of iterations. And we're finding the max of that and zeros, because you can't have negative iterations yet, because we haven't figured out an awesome time-traveling computer. So you can't have negative iterations. Okay. And the thing about this is that Fortran pre-computes this. So if you made an attempt to change the value of I during the execution of the program, it would change the value of the results that get printed out in the main part of the loop, but it won't change the number of iterations. The loop is still going to iterate the exact number of times that was computed at the moment the loop was first entered. And the same goes true for attempts to change the value of start and end. If I were to change this to something that looked more like this, do 10I equals, kj 2, and I had some stuff in here. All right, the value of k and j might change in here, but the number of times that I is going to iterate, and the stopping point for the starting value for I, the stopping value for I, starting value for I will be k, stopping value is when I exceeds j, and the step value is 2. But all this is going to be pre-computed, so the values of k and j are considered interesting as far as the loop is concerned, only at the point when you initially enter the loop. After that, if the values of k or j are changed, even though you do multiple iterations of the main body here of the loop, the number of times that the loop will actually iterate is still going to be fixed, and it's fixed by the initial value of k and j the first time you enter the loop. Okay, so that takes care of the discussion of counter-controlled loops. I've got some notes here about Ada, so I'll talk about that briefly. So not quite done. Should take a look at how Ada does things. So here's Ada's syntax for a counter-controlled loop. For variable in reverse discrete range, discrete range loop, end loop. Okay. And the discrete range, examples of a discrete range might be something like this: 1, 2, 10, or they could be some kind of enumerated type like Monday, ... Friday. So you've got a bunch of choices there. So if I do this, write some code here, for count in 1.5 loop, sum colon equals sum plus count, and then I end loop. All right. Now, if I were to ask you what the value of sum was at the end of the loop, you'd say, oh, well, it's just 1 plus 2 plus 5, which gives me 15. So that's the value of sum, assuming that sum was set equal to 0. And the scope of the loop variable. So what is the scope of count? What is count scope? Well, count has the scope of this loop and the body of the loop here. Okay, so basically the body of the loop. So you can't access count outside of this for loop. Now, remember, Ada is a much safer, more conservative language, maybe conservative language than a language like Java. So, what does that mean when I say conservative? Because I'm giving you guys a hard time on your homework assignments when you don't explain to me when you use a term, I want you to define it. So by conservative, what I mean is, if you can't puzzle out what the answer is to a particular question about how something works in Ada, the answer is you probably can't do it. So the question is, can you change the count variable, the loop counter, in this case the variable count, can you change that inside the for loop? And the answer to that is no, you're not allowed to do that. Count is a special loop variable. It's only used, and it can only be changed by the for loop itself. It can't be changed by anything else inside the loop. Now, what if there was a variable here and a variable here that defined our discrete range? Could you change the values of those discrete variables? In other words, here it was j dot dot k instead of 1 to 5. So the answer to that is, it's okay to change the values of j and k, but they will actually have no impact on the value, the range that count moves through, because the for loop predetermines or precomputes that range at the moment the for loop is encountered for the first time. So it'll say, hey, I'm a for loop, here's count, my counter variable, here's the current value of j, here's the current value of k, I'm going to use those as my discrete range, and then the for loop is off and running. It is not going to, if j and k change inside the body of the for loop, it doesn't matter, count's going to use the original j and k that was encountered the first time the loop was executed. Alright, so that takes care of counter-controlled loops. Now let's talk about logically controlled loops. Or logic-controlled loops. Let's be consistent here. So logic-controlled loops. Even more specific, logic-controlled iteration. So here we're talking about your while loops and your do while loops. So, one question I always like to think about symmetry, and one question I have is, is a for loop can you convert that into a logic-controlled, with a for loop, which is a counter-controlled form of iteration? Can you convert that into a logic-controlled? And I think you can. So let's do that. Int I equals 0. While I is less than 10, I plus plus. Okay. And then how about the reverse? Can you take any logic-controlled form of iteration and convert it into a counter-controlled loop? So the answer to this is it depends. It kind of depends on what form of, or what language you're working with. So in the case of, let's give you an example. So while not user ID dot equals Fred. So there's my logic controlled loop. So can I convert that into a counter controlled loop? Well, there's really no counter here, right? There's no value that's you know, changing over some range of value. So it doesn't make a lot of sense, but yet you can still do it in the C-based languages, because I can say for, and basically, you know, I don't have to do anything. Well, I could do this. I could say, you know, initially the user ID is going to equal an empty string, and then I'm going to say let this run as long as we're not user ID dot equals Fred, and I don't have to do anything here. So I'll put another semicolon. So I'm basically indicating, yeah, user equals Fred, yeah, another semicolon, basically saying, hey, there's nothing, and I don't really have anything to share in this, the update action. There's no update that's happening there. And then there's some stuff that happens in the for loop, possibly which changes the value of user ID. So I might even take that thing that changes the value of user ID and stick that in here as my update action. And then I can check to see if the user ID equals Fred or not. But that's really not what it was intended for. I mentioned that there's while loops and do while loops. So those actually have special names in case you're not using the keyword while or do while. They're called pretest. So pretest, we're checking the control expression first before we go in the loop. So while control expression. And then we've got some loop body. And then there's post test. And here we're checking the control expression after we've executed the body of the loop. I'm trying to remember how I usually do this. I think I do it here. I don't do the do while very often. Again, because not all languages have do's, the post test. And so, since I program in so many different languages, I try to stick with things that I find common in lots of different languages. So, but anyway, there's pretest and post-test. So, in terms of logic controlled, I'll just do a little chart here. So, C-based languages like Java, C++, C, have both pre and post. Ada has pre. Perl has pre. Fortran 77. What do you think the answer is? Take a guess. Just take a guess. The answer is, are you ready? Neither. Or neither pre or post test. So you have to use goto. Gotta love Fortran. There's also additional forms of loop control. So sometimes you're deep in a loop and you find yourself in a situation where you're maybe nested pretty deep inside an if block, inside another if block, inside an else block, in some kind of loop, and you've reached a condition where you want to quit out of the you want to go to the next you want to quit out of the loop. And so how do you do that? Well, here's an example. So for int row equals 0, and then there's some stuff we do with the row, and then for int column equals 0, and there's some stuff we do with the column. So we're getting kind of nested here, and we're computing some sum plus equals some stuff, and if sum based on row and column, and if sum is greater than 1,000, then what we'd like to do is break. Now, if we do that, what's going to happen is that will kick us out of the inner for loop. This is the way Java would work. This would break us out of the inner for loop, but it doesn't get us out of the outer for loop. And so if we need to kick out of both loops at that time, what we're going to be left with is writing a second if statement that says if sum is greater than 1,000, then break. So we're repeating these statements. Really what we'd like to do is just kick out of both of these for loops. So this is a common enough problem with nested for loops that C# offers an alternative. So I'll show you C#'s alternative, which is pretty neat. It's going to use some awesome copying power here. Yeah, I don't know how this is going to go. Yeah, it didn't seem to work. Alright, let's just do this. I'm just going to copy all this again. Okay. Copy. I'm going to go over here and paste. Alright. And slide this over so you can see it. Okay. So instead of doing break here and instead of doing this, C# actually allows you to construct labels. So I can create a label here, both loops, and oh, sorry, I have to say break too. So you say break both loops. So if sum is greater than 1,000, we're going to break both loops. And then I can create a label here, both loops, which kicks me out of both for loops. So that's pretty cool. I really like that. There's another form of iteration that shows up, which is data structure iteration. And you've encountered this, I'm sure you've encountered this in Java. So there used to be a kind of an awkward way of doing it. So let's say I had an array list, and I'm going to show this to you in, I'm just looking in my notes here to see if I want to show it to you in C# or in Java. I'm looking here. Hang on one second. Okay, so all right. So in C#, in C++, it would look something like this. So here's my array list. And then I populate this. So let's assume I populated my array list. All right. So I'm done populating it. Now, how do I get access to the elements of the list? Well, one way is, one of the problems with array lists is that they're not really arrays. They're, they're dynamic arrays. They can grow and shrink, and so I can't index the elements of the array list by saying this list sub 5, let's say. That's not okay. I can't do that. So if I want to get the fifth element of the list, what I'm going to have to do is iterate through the list elements until I get to the right one. Now I could do that with a with a while loop. I could say int count equals 0 for sorry, not 4. Oh yeah, I guess I could use 4. So I could say for int, let me just do this then. For int I equals 0, I is less than 5, I plus plus, and I might say something like, oh man, this just gets messy the more I mess with it. So like, oh, let's call this value let's do this. So I'm going to say we'll assume we populated the list with strings. I'm still changing my mind here. Okay, here we go. So let's say we populate it with string arrays. All right, so char star value equals null. So we don't know what the value is at the fifth element, but we're trying to get to it. So I'd say for int I equals 0, I is less than 5, I plus plus. And okay, so then what I'd do is I'd say current equals list subhead. That's the start of the list. And then I'd say current equals current arrow next. Okay, so I need to change this to 4 if I wanted to get the fifth value. Alright, so we're going to keep doing this current next, so on and so forth, until I end up with, I exit with the value of current. And at this point, current points to next, or the fifth value. And I could say node. I guess I call the fifth value node, and then I could say, value equals next, or sorry, current value, or data. Maybe we'd say data here. All right, great. So now value holds the data part of this array list node, and I went to the fifth array list node. Okay, so it's kind of a pain to set all that up, and so what developers did in the first iteration of trying to fix this problem, basically traversing a linked list here. and it's awkward. So the solution to this initially was to create kind of an object-oriented enumerator type, and it looks something like this. You would say for enumerator star I, there's my I again, and then star I equals list dot or list arrow get enumerator. So the array list object has the ability to return an enumerator for it. So that's the first part of my for statement. And then I'd say every this is kind of clever, but you say like I arrow next, and then you didn't have to do anything in the final part of the for loop because there's no update. This check next would return true if there was another element, and it would return false otherwise. And then what you could do is you could say cout I sub current sub data. So that would get you the data out of it. So I is the enumerator. We're saying we're interested in going to the current data element of, or the current node of the enumerator, and then from that node we're interested in the data element of the node. So there you go. Well, that's still pretty nasty. And so some languages came up with something a little more elegant, and that is this thing called the for each statement. So I'll show you what it looks like in Java. So let's say you have get my notes for this here. Okay. So let's say you have a list of suits. So here's my suit type, suit variable, and that is from in a collection called suits. So this is my type. This is my variable. And this is my collection. And then I could do that again. So for rank colon ranks. So again, this is my type, variable, and collection. So this is a collection would have been set up beforehand. These collections would have been set up beforehand. And then what we're doing is we're basically having the outer for loop and the inner for loop iterate over their respective collections. And then we could create, maybe had an array list called deck, and I could say deck add, and then I could say new card suit comma rank. So this is really nice. It's a dramatic departure from the two examples I showed you before, where we were trying to move through these collections using some generic mechanism, but it just really got awkward and it was really distracting from the core point of the code, which isn't really to move through the collection, was to do something interesting as we move through the collection. So, and these aren't for, these are for, oh, they are for, yeah. So it's a flavor of something that used to be called a for each statement. All right, cool. So that takes care of data structure iteration. Well, the last thing I wanted to talk to you about was something called short circuit evaluation. So you have to watch out for this when you're writing code. So if I write something like this, while index is less than length and list subindex is less than or equal to key, then do some stuff. Okay. So the situation I could get into here is if the value of index exceeds the length of the array, and if that happens, or is equal to the length of the array, in which case, for a zero-based indexing an array, we're out of bounds. We're going to run out of bounds if this expression is allowed to execute. So, why is that a problem if I'm testing it here? Well, it's a problem if I'm testing it here if the language doesn't use short circuit evaluation. And that's because we don't know, since this is an AND, it doesn't really matter which Boolean expression gets evaluated first. Does the Boolean expression A get evaluated first, the Boolean expression B get evaluated first? As from a mathematical standpoint, it doesn't matter. From a programming standpoint, it very much does matter, because if we can have A evaluated first and it returns false, then we don't have to evaluate B. So if we could have that mechanism in place where if A is evaluated first, returns false, it's just a waste of time to evaluate B, then we won't run into index out of bounds errors. So some languages have short circuit evaluation in place, some don't. Some languages might use short circuit evaluation if debugging's turned on or debugging's turned off, or optimization is turned on, or it may depend on the optimization level of the language. So you have to be very aware when you're messing around with a language whether the language uses short circuit evaluation or not, and it's a big deal if you're messing around with loops. Alright, that takes care of short circuit evaluation and loops, repetition, iteration. I think that is the last thing I wanted to talk about. So there you go. Have fun, and I'll see you guys on Monday.